as such, right? In the reactive world, we can largely kind of, within Java, we can kind of largely broadly kind of categorize into like different areas. And there's reactive programming, reactive systems, and then reactive streams. So let's first then about reactive programming. I mean, as such too, reactive programming, we're talking about really the, individual components. How do we actually, implement like a component? For example, in reactive style of systems of programming, it's basically we're dealing with like a microservice, for example. How do we kind of do programming? What is reactive? Essentially, too, it makes use of a very functional style of programming. So that's why, too, I think when Java 8 came out, it was actually, the time was ripe, and for like, kind of Java to support reactive programming even more, because it does require a functional style of programming. It's not exactly functional programming. The difference is that in reactive programming, we're talking about events that are traveling through, carrying with it data in your system. So it's a bit of a more abstract sense. So data travels and the state changes. So whatever is changing the state of the data, that's what kind of drives your logic forward, is really the change of state of your data. However, like for functional programming, we're talking about a thread, of control in your program. So basically, too, is that your function, your functional style, and then, any kind of changes, in your thread, or kind of your thread keeps going and keeps, the execution thread essentially is what drives the program to go forward. So that's kind of a bit of a difference, but I'll get more into detail. And then for reactive systems, so in order to qualify a system to be reactive, it must satisfy the 4 principles. And I also go into it about the reactive manifesto. And then there are also like, architecture that applies to reactive systems. And as such, reactive systems is of a more higher level description of a system, not just description, but a higher level kind of, peaceful coexistence of, all of these complicated components within a system. And reactive systems must satisfy the 4 conditions. So, and then the other thing is about reactive streams, and which is why I named the talk is more like about streams, because reactive streams is really a specification that comes out of this whole movement. It attempts to define a standard, a specification, a standard to manage like asynchronous data streams and also manage back pressure. And that's what reactive streams like aims for. There's a specification for that. And it essentially is based out of Java 9, the Flowable API. That's what it comes out of. And so I'll go into a bit more detail. Okay. First, let's then talk a bit about reactive programming again. When it comes to reactive programming, we are really dealing with streams and streams of data. So it's like kind of different than the traditional way of imperative programming. So reactive, it deals with like declarative style and dealing with streams. So these are, this is a diagram that I actually borrow from the, or actually I should say I borrow from the Reactive Extension RxMarble website. So it's describing reactive programming. Think of it like a stream. So you can think of like the top one is stream. So stream travels and it travels in time. There's some time element too, it deals with events. The top one is basically a stream that's awaiting events, though no events happen. The second one is there are events, then basically there's a perpendicular line. And that one essentially is, it signifies the stream has terminated. And the third one is an X you see over here. The X is actually signifies an error event. So an error event in reactive programming is a first-class citizen. So unlike, imperative style in which, you have error condition, you need to like catch the exception and all that. No, but in, well, we also like catch, in how you do coding, but the way error event is being treated is like same as any other event. So it's kind of a first-class citizen, so to speak, error event. So in here is that an error occurs. So it basically blocks the stream from going forward and must be handled. accordingly. And then the bottom one is basically an open-ended stream. You see that there are events coming in, and then events happen, and data gets transformed, but the stream remains open to receive new events. So, and let's take a look to an example of an RX Java example, and this one, I'm using this a very commonly used transformation operator on a stream. So this one is map. So map essentially takes like a function, think of math, in mathematics, you pass in some function, you define the function, and basically then, input comes and you transform it. So in this case, this example is map, and then transform this, whatever number that comes in, will multiply by 10. And so you see this, this is kind of simplest case. And oh yeah, somebody asking, Uday, yeah, RxJS, yes. This specific example is actually this RX Java. Yeah, but all based on Reactive Extension. Yeah, extension. So the RX, yeah. That's right. That's right. Yeah, exactly. So yeah, so thanks for asking. And so yeah, this is like, but in terms of like syntax, right? RX essentially Reactive Extension. Let me kind of step into it since you were asking. So Reactive Extension came out of Microsoft. That was like RX.net that actually was born first, about before RX Java, RX Python, RX Scala, RX here JS too. And Netflix saw that, the potential. That was like back in like 2010, the early 2010. So Netflix actually took the RX.net and ported it to Java and released it in 2013. That's when RX Java 1 came out in that time frame. So then later too, then there are other language frameworks that also like ported it, right? Like I mentioned, RX JavaScript. So over here too is an example, yeah, map. So you transform. So the transformation here specifies that you multiply by 10. So if you look into the code, then we have like, by using like, RX Java 1 kind of a semantic, right? And so it's also RX Java 2 also. But I want to say RX Java 1 because observable is not, it doesn't support, by nature, I think it does not support back pressure. So RX Java 2 has flowable, which actually it's just like observable, but it supports back pressure. But anyway, so this is observable, and doing a dot just is like taking the input, right? That's what you take the data that comes in is like producing, the producer. And in this case, there's 1, 2, and 3. These are the different events that carries with it some data. Then you apply the dot map operator to it. So it transforms your data. And then immediately too, you want to do a dot subscribe, excuse me. So dot subscribe is like the consumer. So think of like within one statement, it's actually you have the producer, transformation, the processor, and then the consumer all within one statement. So that's kind of a reactive programming style too. And so you transform them, and in this case, all it does is it takes the resulting data and print them out. And Timber is like just system kind of output kind of print line statement. And basically too, it outputs, and you see from here, 1, 2, and 3 will become 10, 20, and 30. So if you visit like rxmarbles.com, you can get more like practice too, like interactive practice using the different operators that are available. And so map is like a very basic one, and that's being used quite frequently by different systems. And there are also, for example, filter is also another popular one. It's like large, especially in large data processing, and think of how if you compare with imperative style, then it's more efficient in some sense, from a semantic, how we kind of structure our program, because what used to be imperative, then we'll have to do like if then else type of statement. You have to like you have to break up your whole processing into different statements. And in this case, reactive, you can do it in one command. Essentially, you chain them together. But used to be we have to do like if, so you be testing, some data coming in, you have to kind of like basically extract your structure of data and then say, okay, if, For example, like if age is greater than 10, then you do something, or if it's less than 3 or something like that, you use a filter type of operator. And other operators are like merge, and for example, like map, a flat map, and all those. So this is like rxmarbles.com. So in this particular talk, I won't kind of get more into all the details, but you can always like look into it. So, look up the rxmarbles.com. So, okay. So now, then we move a bit. Then that was a quick intro to reactive programming, and let's get more into the reactive systems aspect. So reactive systems essentially is like one step up, from just the programming aspect. That in itself, the programming is quite complicated, dealing with events, asynchronous style of processing. And here too, when we talk about reactive systems, we're really talking the system as a whole. So imagine, right, you have to, well, last year, if you came to my talk, if you're in Bangalore, not sure if you came to my talk, I was using an example, right? I mean, not quite exactly that example is, if I crossed the street in Bangalore, I remember there were no traffic lights. And so you have to like dash across the street, think of, all of these individual components in a system. It's like all the cars that are driving. The idea is that you don't want any crash to happen. So, in some kind of crude way, I'm describing a reactive systems is much like a traffic, they each individually are operating, but you want the mechanism so that they don't crash, with each other. They are all like doing the right thing. And so in a computing sense, of course, it's more complicated because then you're talking about maybe you have data that are being shared, among different components and such. So, okay, back to then reactive manifesto. So these are the 4 tenets of core principle of reactive systems. They need to be responsive, and meaning that requests needs to be handled in a very timely manner. That's being responsive. And then there's also resiliency. Now, also too, when I talk about responsive, what can make it happen? It's basically you're increasing the performance of a system so that can be handled. For example, in the modern day architecture, we have cloud now, containers in cloud. Those actually helps in like the responsiveness of a system. So let's kind of take a look. Okay, let's then go to the left side. Let's take a look at elastic. And elastic capability means the system has to be very scalable. And so if there are more requests coming in, you want the system to be able to scale. There are more processes to handle all of these requests that are coming in. So I like to use an example of e-commerce. Yesterday too at my talk, if you came to it, I kind of use a Valentine's Day kind of shopping cart, kind of a flower shop. And so, the day before Valentine's Day, the flower shop, the e-commerce site will get a lot of requests, lots of flowers requests. So you want the system be able to kind of handle the spike in traffic and requests. So then you need the system to be able to still be responsive. Then the elasticity is really important because then it means you have more processes to handle all of the requests that are coming in. And then if there's like slow time, for example, maybe like summertime, people are out and doing something else, then you want, most likely you don't have spike in traffic for flowers. And so, so then you don't need to have many processes running. You can just maybe keep one thing, some kind of order receive, kind of a, system in a component to be running as opposed to 10,000 or something a day before, like a heavy ordering day. So. Okay, and then the other thing is dealing with resiliency. So essentially, these are dealing with like recoverability of a system in the case of failure. So that's also a very important aspect of a reactive system. So in order to qualify for that, you have to have some level of resiliency. For example, in ARCA, Lightband ARCA system, it has its supervisor capability. It's essentially too, if there are some, child actor. So think of kind of actor and they can spawn off children, kind of child actors. So if any kind of problems are occurring on any of the children, then basically their supervisor capability, you have to notify your parent, right? The parent that, okay, I'm having, trouble doing something. And so then your parent will need to respond to it, or there's some error occur. Then you don't want that to be blocking the whole system. Maybe you want to spin off another child to handle requests while you deal with the one that's having problem. kind of, so in a sense, it's kind of resiliency, recoverability of a system. You don't want responsiveness to degrade too. The performance still needs to stay the same. And so all of these are possible because of, you know, the message-driven aspect of a reactive system. Message-driven indicates that they're always like a request kind of response type of scenario in which your messages have a destination. So so these are like message-driven capability. They are all like, you know, everybody is communicating through messaging. And so that kind of also indicates that your system are very loosely coupled, not tightly coupled, and they can all be passing messages to communicate among itself. And so let's then take a look at the next one. And let's get a bit more too into like what reactive systems is really trying to address. Essentially is concurrency. So, and you may also be wondering too, like why reactive systems, right? You can actually, you know, have hardware, for example, in your cloud too, you can, you know, deal with like having hardware, or they actually before cloud, right? You used to, well, we were kind of like handling system kind of in your data center, you know, you have more, you add more hardware to it. But the idea is that right now hardware is becoming more kind of what you call like more sophisticated now. And so now we have multi-CPU systems, and we have multi-core kind of you know, processing system. So all these, right, they're kind of making the time ripe for reactive systems software to kind of get caught up with it. So the problem is trying to address is really concurrency. So dealing with multiple tasks at once is really concurrent systems is meant to be. Now, in some ways too, it's dealing with multiple tasks at once, but it doesn't require your system to be multi-core or multi-CPU. You can still have like one processes and one process, just like I kind of often think of myself, I'm having so many things to do. I'm like a computer, my mind is like a computer itself. I may be doing multiple things all at once, but really I'm concurrent processor because I can only deal with one thing at one time, you know, unlike, you know, parallelism. Parallel systems are really relies on having multi-core hardware, because then that will mean you really can truly handle multiple tasks all at once. You know, they're all CPU and basically, or you can have multi-core within your hardware, then that really can handle parallelism, really truly parallel. So, okay, so that's the kind of goal of reactive systems. And also too, wanted to point out too, in reactive systems, now thing is, nice thing is that then it, because of the library itself, it actually it's being designed so then us, right, as programmer, developer using it, we don't actually have to worry about threading. We don't have to deal with the threads directly ourselves. But that doesn't mean there are no threats, you know. Then there are people asking me, well, you know, because I'm actually, I'm doing a Twitch live stream, and actually I'm making use of executor service, right, to handle some metrics, you know, in my system. And they were like, well, then you're using threats, and you were talking about why, you know, in reactive systems you're not dealing with, you know, you're still dealing with threats. Be the thing is, like for that particular example, I actually is dealing, I was kind of handling some metrics too with that. But that doesn't mean, you know, you can't be using threading service. But the thing is with reactive systems is that threads are being handled in the user space, as opposed to the old style of imperative style of programming. If you remember, you do threading, it's basically all of the threads are happening in the kernel thread. So it's only like one thread. So you can imagine too, back then it used to be take more time, because if you have threading happening in the, you know, on your IO main thread, then it basically would mean that, you know, it has to block, right? Anytime you're doing something, you know, something else happening, you're kind of multi-threading, but you have to, your main thread will have to be blocking. And there are also a lot of context switching happening, kind of going between like different tasks that is happening. But now you basically, in reactive systems, you move all of your threading, all the concerns into your user space. So that way too, you free up your IO thread from not having to deal with kind of more, so to speak, like application level kind of threading. And also too, again, the threading is being done mainly by your system itself, by the software. So then you don't have to worry about it. For example, like Vertex, it has an event bus, so it handles all of the threading inside in the, you know, in this on their system level. So then you don't actually have to worry about it, not directly yourself. So, and that's that. And so let's then move on to the next one, which I like to bring up too in reactive system. There are also reactive design patterns too. So I'd just like to highlight a few among others, and I have a link to it towards the end of my, this set of slides that has a link to like reactive systems patterns website that has a very good discussion of all of the design patterns. But these are the ones that we are probably more familiar with, and I like to highlight. Actually, first of all, I like to highlight too. There's a back pressure. So essentially, too, I talk about reactive streams, and reactive streams is a specification, and it aims at like handling a synchronous call, but the main goal of it is basically to handle back pressure. So, and back pressure essentially is the situation in which you have a lot of requests coming in, and then you're basically requests coming in, and whoever is consumed, if you have, well, in ordinary scenario, right, you may be having small number of requests coming in, and then the consumer will be consuming it without any problems. But in situation in which you can have, for example, a spike in your e-commerce system, and then you have a lot of requests coming in, and basically that builds up the back pressure. And so then your consumer will be kind of like overwhelmed by it. So then there should be actually mechanism to handle all of this back pressure. So then you don't like overwhelm your system, your processes at any one time. And in the case of if you are deploying a systems to a cloud, to a containerized kind of like cloud deployment, you can actually kind of design your system so that there may be like more processes to handle. So it kind of relieve all your back pressure. Or maybe you can slow down the requests coming in. Maybe you just kind of make your requests somehow like wait, before you actually give it to your consumer. For example, you can also do that too. But essentially that's back pressure. And then if we go back to CQRS, it's also another design patterns that are used in reactive systems. And CQRS is command query responsibility segregation. So essentially, too, you're separating the write, in any system, you're writing to the system and also the reading from it. You're separating them out. You separate the concern. And that's kind of a commonly used design patterns, too, in reactive systems, or that we can use, too, I should say. And CQRS, too, very often, too, kind of being used like pairing it up with like event sourcing. Event sourcing is basically you want to store all your events. So in general, right, in the traditional style, we have events that are happening, and we kind of store the data on, let's say on your database, you capture all of the events, and you store all of the data about an event in your database. And so the idea is that you don't want to actually store the state of your data like as such in the database. So you basically use an approach is event sourcing. It's basically you are storing all the events itself. And so basically if you need to like trace back to see what has happened and see what data is happening, you do need to do a replay. So you basically you're keeping track of all of your events, and then you can do like a replay of what is happening. Then that's how you can find out about the state of your data that way. So it's a different approach, and it's also pretty often like used in a reactive style of systems too. Okay, then I talk about back pressure, and then there's also circuit breaking. Circuit breaking essentially it deals with like recoverability, resiliency of a system. So if there are any error that occurs, it's much like a circuit board, right? If some signals have problem, you basically break that so then it doesn't propagate, the error doesn't propagate to the rest of the system. So that's circuit breaking. So very often too in reactive systems, you see these, these four kind of patterns are kind of commonly used. And other ones, for example, they're like saga pattern, or there's also the CAP theorem with dealing with eventual consistency. So you might also have heard of that. And eventual consistency is really dealing with data, in a request kind of response systems, right? Well, all systems are request and response, and we need the system to do something and we expect data to come back. So very often too, we're probably dealing with data. So eventual consistency, meaning that, if a system has to satisfy the four core principle of a reactive systems, there's responsiveness, recoverability, elastic, and also message-driven. But on the responsive side, basically we're saying that it is okay sometimes to sacrifice consistency because sometimes if you need data to come back quickly, then maybe you have to maybe check because data keeps, let's say in a system you're writing data to to the database very fast and all that, and at any one moment you want to like request some data, you want to make sure the data is already like kind of in a kind of like an accurate state. But sometimes it is okay to sacrifice a bit of accuracy because you want the responsiveness. You don't want to wait for it to verify. And at the same time too, what this eventual consistency also is talking about CAP theorem, in which in any given time you always would have network partition. Your data needs to be connected to the network, and you need responsiveness, and you also need accuracy. So they can't always be satisfied, these three conditions. So it is okay to sacrifice a bit of the data consistency. So that's kind of eventual consistency. Then how can you actually achieve accuracy is if you kind of wait, take enough time, then basically the data will become consistent over time, because the write to the system will slow down too. So then your data will eventually become consistent. So if you query it again, it should be the accurate data that you're expecting. So anyway, but that's also another pattern that I thought I'd bring this up. Okay, now then let's get more into like streams, reactive streams and streams processing. So when it comes to streams, then there are essentially two models that we're talking about: push model and pull model. So think of your data traveling through a stream. Okay, so all right. So I was gonna say, well, there are push streams, and push streams too is often also being described, especially in RX Java. RX, the Reactive Extension, RX world, is basically hot observable. So by meaning hot is that if data comes, it's basically the data will get pushed to downstream. It gets pushed, and it doesn't probably as concerned with what's in the downstream. It's more like it's emitting data, right? Your source is having some data, and then it is kind of actively kind of giving it to whoever broadcasting, sending it out, kind of like that. It's basically upstream pushes data to downstream. The producer produces data and give it to the consumer on the downstream side. And in an event-driven kind of messaging, very often is that the data comes, but it doesn't have unlike message-driven, it doesn't have an address telling it where the data should go to. It's more like I'm just broadcasting, giving it to you. Whoever wants it, you have to be responsible for subscribing to it. So that's kind of more like in an RX kind of world, you have to do a .subscribe. So that then comes to like a pull model. Pull model is really like downstream. That's basically pulls data from the upstream. And that's also being described as a cold observable. It's a bit more like a lazy kind of way of getting data. In this case, you're just like the consumer needs something, you just signals, oh, I need some data that will happen in the future. And then, I don't really go and get it myself. I just some kind of signaling. So then like when data comes, then basically you have some subscribe. So it knows then when it comes time for the data to be pushed, then you will get the data. So it's kind of like a cold observable. It's being kind of described as. So okay, so let's kind of take a quick look at the push kind of in the picture. And here is that producer emits data, and it sends the data without being asked explicitly to the consumer. So it's like a producer, consumer, or publish and kind of subscribe kind of scenario. And you kind of go from the source to the receiver like that. And like I said, push very often too, it sometimes emits data without actually kind of knowing whether the receiving side needs it or not, kind of scenario. So for example, like in push, for example, like your cell phone too, very often, right? With cell phone, we have like push, push kind of thing, in which we're not asking for it, but maybe in your cell phone provider, it has certain like updates that are being pushed to your phone without you asking, sort of like a push model in that sense. So, and let's kind of take a look at pull. So pull is again downstream, consumer needs something, and in an RX extension, right, world reactive extension will be like a subscribe. Doing a .subscribe in there is kind of a pull and then push kind of way, because you're pulling data, you're saying subscribing to some data that will happen in the future. So when the data comes, then the producer knows and it emits data. it will actually then be pushed. So in some ways, pull in the reality is more like a pull than push kind of model. So when you pull, you signal you need something, and then it gets pushed to you when the time comes, when the data is ready. And so, and the thing is with reactive streams is very often their implementation is actually more like a push or pull than push kind of model. And that's what it uses too. So, okay. And okay, and now then let me again talk a bit too again about back pressure. I'm kind of using some diagram to explain it. And here is not actually that good, but I was trying to draw it. But I thought to show is that there are too many, like shower, for example, water coming in, and it's kind of feels like water coming in at you, and you can't handle it. And it's basically pressure coming to data coming to you. Basically, it kind of get pushed back, kind of like that. So. So that's an example, and this actually probably is also another kind of more accurate picture to describe back pressure is publishers publishing a lot of data coming to the subscriber, but the subscriber can't handle it. It's kind of like overwhelmed by it. So basically, publisher generates more data than subscriber can process. Okay, and some kind of more concrete thing about the publisher subscriber reactive streams is basically their reactive streams are actually just specification, and it doesn't. It's based on Java 9, and all it has are 4 interfaces. It doesn't have any implementation, so it's kind of it's being deliberately kind of designed that way. So then it's being used by service provider. So these are actually reactive streams in general. If we're writing applications, very often we don't implement reactive streams ourselves, because you can imagine too, if you're implementing yourself, it does get quite complicated, even though you think, oh, only 4 interfaces, but you actually have to handle the back pressure, and that's where usually the bottleneck, the difficulty is challenges, right? In kind of this kind of asynchronous event-driven back pressure scenario. So you want to rely on some libraries that supports reactive streams. And these are the 4, publisher, subscriber, processor, and subscription. So a little bit closer to that would be like this particular kind of interfaces that I can show you. So there's publisher, and it has a subscribe method, and then subscriber has on subscribe, on next, on error, on complete. And so now the subscription interface is essentially is a bit more abstract. It's basically a subscription that will it will happen when there's a publisher and subscriber being kind of associated with each other, and that's a subscription. So that's also where back pressure support will happen, is on the subscription. Kind of on that level. And then there's processor. Processor essentially too, you see it extends the subscriber and extends the publisher. So these are like the 4 interfaces. Okay, and okay, let me go to the next one. Okay, so that's reactive streams. I already spoke about it. It's basically, there's no implementation. It is a specification out there. I think currently maybe 1.3 or 4 at this point. And there's a TCK, so Technology Compatibility Kit. So whoever wants to implement reactive streams and to be qualified for it, it's just like any other standards and specification. If you want to qualify for that, if you're a service provider, you write the library, you have to actually pass the TCK, like the test, the Technology Compatibility Kit tests in order to qualify for it. And so the nice thing about reactive streams is that it defines a standard of how back pressure should be handled in an asynchronous, non-blocking fashion. And so if you can imagine, right, it's actually your creativity is unlimited in here, because if you're trying to write a system, you can actually write it using different libraries or handling different parts of a system. They are all, maybe you have some legacy code, for example, you want to convert to some streams, or somehow you have legacy system that produces some data, you want to process it, and you might say, well, I want to modernize my system. So in modernization, you don't necessarily have to rip out whatever is already working. For example, maybe something in your older like MQ series, or for example, some queuing library, you can maybe plug it in and kind of connect to some, like newer ways of handling reactive streams. Like these are the commonly used reactive streams library, more popular ones. So You basically can write different ones because if they all kind of follow the same spec, you basically can build up a system. You can build up the pipelines that are essentially like written in different libraries, and some are even like older, like I said, MQ. And you can also like, mix in maybe Spark, in a machine learning language, machine learning kind of application. So you can have different ways of handling the streams of data, and in your whole system, you can actually build out your pipelines using different ways too. So these are the ones, Spring Reactor and RX Extension. These I grouped them together because they are the same engineering group that design and develop it. David Knopf that is leading that. So RX Java 2 is when the Spring Reactor guys, the Spring Web Flux Project Reactor folks came together and they work on RX Java together. So you find their set of operators are very similar. And also RX Java 2, because that's when they started supporting like Java 8, and Spring Reactor started off supporting Java 8. So that's that. And then there's also Vertex. Vertex, I did a talk earlier today, and that's actually one. Vertex is a very lightweight, event-driven library. And it's actually quite fun, to be coding it, because it's somewhat of a simple way, even though it's not really that simple, but it's kind of, it can do a lot of things to it, and it has its own event bus, making use of a vertical model. And so it actually helps to do microservices serverless deployment quite easily using their your system implementing all of the verticals. It's much like Akka Streams, right? And going to the next thing. Well, Akka Streams itself, it's actually a streaming package, right? That's based on the Akka kind of model, actor model. And basically, Akka comes out from Lightband, the company that Martin Odersky, Dr. Martin Odersky started, and with Scala. So that's Akka Streams. And Akka Streams itself, it implements Reactive Streams too. But interestingly, it's because Akka is quite sophisticated, it has its own way of doing things. And I'll go into a bit more details. And then there's also Microprofile. I believe my colleague Emily just did a talk on Microprofile too. So Microprofile essentially is catered more, is an enterprise EE kind of with that goal in mind. And it has, it's kind of more designed for cloud native type of microservices deployment. And also last year it started supporting like Reactive Streams, that spec too. So it's essentially too, it has reactive operators and then reactive, the microprofile reactor operator, microprofile reactor messaging too. So they're just separate libraries. And I think they might be coming out with a third one, some libraries too. I just don't remember, but anyway. Then there's also RSocket. Now RSocket is a very interesting library too. It's more lower level, it's a binary protocol. So I'll start going into details of that. Okay, first let's kind of go back, right? The 5 things, and there's Spring Reactor, the pivotal. It comes out. Oh, it's actually VMware now, and I was having these slides before VMware kind of merged with Pivotal, but it's actually VMware. And very often, if you write, your reactive code, you're making use of the reactive core library, and as the project reactor, right? And there's also Spring Web Flux, and so Spring Web Flux essentially is the web framework, and then project reactor is the reactive library that Spring Web Flux make use of. So, and then there's also concept of the flux. It's basically handles 0 to many items in the stream, kind of, or 0 to many streams, right? And then there's also mono. Mono is 0 to 1. So that's something I want to highlight. And actually, too, then there's RX Java, which I earlier gave you an example. So that's also an API for asynchronous programming. It's very popular and it's used by Android app a lot too. If you're doing Android, you're aware of RX Java, and right now it's Kotlin. I think there's also RX Kotlin as well. But of course, Kotlin works with Java, so RX Java. Basically, I also describe observables. They're essentially handling streams like on the producer side, the observables. And then flowables came out of Java, RX Java 2 that has back pressure support. And then there's Vertex, and Vertex is what I did the presentation on as reactive framework. I mentioned about vertical model, and Vertex has its own event bus that handles the event. So each vertical actually has 2 threads in handling the event within the event bus event loop. model too. And then there's the vertex runtime, the control center too. And I will quickly show you some code too, in a little while. And then there's Akka streams. And again, I want to bring up Akka streams. It's a bit of a, kind of a different, and the light band folks are always operating on a different kind of mentality because, well, it is a very sophisticated framework. And as we know, it's not that simple to understand if you first study about it, because they are actually very clever. But also, just don't get discouraged. Sometimes Akka might be a bit harder to understand, I think. But the thing is with Akka too, the way it is being deployed, it's actually has a dependency on always you have to deploy to the cloud too, and that's how Akka would run. And Akka streams as such, it implements the Reactive Streams interface, but it's actually it's decoupled from that. It still actually implement Reactive Streams underneath the hood. But the thing is, it has its own way of defining, your source and your destination. For example, in your pipeline, you have actually the your data, the flow, and then it's basically flow through like your process and then go into a sink, right? And it collects all the data. If it fills up, then that's when data will be ready, kind of thing. So. And basically, Akka streams, they were saying that, well, we don't want to just have exposed, these push or publisher, subscribe, all these methods, but they have their own API that's minimal and consistent, and they emphasize explicitness over magic and compositionality, which actually you can combine the pieces and retaining functionality of each part of your system too. And again, very loosely coupled, very much of a they're all like tied together using the actor model. And actor is essentially, you always make use of the mailbox. You always have a sender and receiver in any kind of mailbox scenario. So it makes use of its own kind of messaging kind of way of doing things in their actor model. And it also has a lot of tooling too to handle stream processing concern like back pressure, buffering, and transformation too. So, okay. And then now, microprofile. That's basically primary focus is on microservices and location transparency, temporal decoupling, and basically microprofile is strongest point is that it has a very good integration with OpenLiberty, and like OpenLiberty is our open source web sphere, and Emily, who just did a presentation, and she's the architect of OpenLiberty, or one of the architects on OpenLiberty. So microprofile is essentially is an open source project, and it has good handling of like reactive streams these days. So just kind of give you an example too, the microprofile reactive messaging is basically, it's relying on annotated methods too. So you can annotate your method with marking it outgoing or incoming. And then they all travel. These methods are connected to channels that are named channels. So in this case, it's an example of the method A has an outgoing order and a channel. Then it travels, and then that's how it kind of can travel. The data travel between the different methods, and you can have like an incoming. In this case, right, it's showing that the incoming is the order. From the order channel, and then outgoing to status, and that's how they kind of like all connected, and they are all matched up by channel names. Now, then there's RSocket. So RSocket is really binary protocol. It's a bit lower level than the rest that I've previously discussed. They are being used on byte stream transports too. They are essentially 4 models. Their request response, which is like 1-to-1 kind of model, or 1-to-0, which is fire, your requests get fired and forget, you don't expect any response. And then there's also 1-to-many, which is a request and then expecting streams, in the response. And then there's also this channel. Channel stays open, it's a bidirectional, it travels, both ways. You can have requests going there and then basically response coming back, and you maintain that connection too, as the channel bidirectional. Okay, and here is it's a slide that I borrowed from the Spring One platform, and it's actually from a Alibaba advocate that I co-presented with, and he has this, and he said, yeah, I can use that. And I just thought this is a good way of showing RSocket. So if you're kind of thinking of any kind of making connection, in your code, utilizing like a reactive library, you can think of like using RSocket. It is kind of a relatively new library, but it supports like reactive streams, and it's also very flexible. You can have clients that are available. It's available for all kinds of languages and platforms too, and supports like reactive back pressure, streaming, resumption, cancellations, all of these, and it's faster. It's on open source on layer 5 and 6 communication protocol. So it's a bit kind of a lower level. But the nice thing about it is that you don't need to worry too about like the configuration kind of needs, because it actually does a lot of these things quite nicely for you. So, and actually I did a talk too with one of the RSocket engineers. This is all open source project too. I did a co-presentation. I did a couple of times. It's on actually demonstrating how, in what scenario can we use RSocket. And we were like training using like streaming of data using reactive streams, and basically feed the data into a multiplayer Pac-Man. If you're a gaming person, you know about Pac-Man games. So basically too, we want to do real-time kind of machine learning data feeding into it. And as you know too, if you're also machine learning folks, and also something I'm finding out too, a lot of the machine learning data, it has to process huge amounts of data in order to be able to, to kind of have your model be trained, right? So a lot of times they are doing it, batching it up. So it's not very efficient, right? Everything you have to wait, you have to take the data and then clean it and do all these things and then batch it up and process. And then you can see too, then you cannot get like a, kind of very interactive way of processing your data and immediately being, training your model and like that. So we actually use RSocket to train the model, and then to kind of play using a multiplayer, training a multiplayer Pac-Man game. And that was actually, you can tell the difference too. It's actually very efficient. And if you compare with the traditional way, there, it can't beat it, right? Because you're doing real-time data processing. So I think there's a lot of potential in having RSocket to work with like machine learning capability. Because right now too, for example, like Spark and Apache Spark ML, those are also, if you want to do asynchronous, I think it requires a different library. It's a bit kind of less convenient in that sense. So, but that's, again, is just giving you an example of how you can use RSocket. And there's also then one more example is an OSGI. It doesn't explicitly support reactive streams, but I want to point out, because OSGI, as you know, is the library that's behind like the Eclipse IDE, right? The OSGI framework. And there's also a push stream specification. Now that one is a true push, making use of real push streams, and it's a self-implementing API too. And basically, the nice thing about this is that you can use this push stream, and also it does rely on OSGI Promise, that framework too, because they kind of work hand in hand, and you're dealing with data that will be generated right in the future, and it makes use of the Promise kind of framework. So if you want to use that, you can use it independently of other OSGI specifications and framework too. And this is kind of a quick comparison. The thing I like to point out is that in push streams, you can basically, it actually allows you to auto-close your streams too. So after processing, you basically can essentially like close your stream. But in reactive streams implementation, in general, you just have the subscription, but you are up, you are kind of at the hands of your library itself to kind of close the streams itself. But push streams is interesting. You can actually have control over it and have the auto-closable set up too. Okay, and oh, I'm sorry, it should be here. So now I come to some sample use cases. I think I kind of talked too much, and I kind of maybe like a little bit tighter, but I already actually, if you came to my talk, there's also the Vertex that I demonstrated. But since I'm kind of running short in time, let me kind of go back to showing you some quick Vertex code too. Okay, so and just for kind of giving an example of for example, like, right, whenever we do any kind of code demonstration, we like to do hello world. So this is an example of a hello world using Vertex, right? And so again, Vertex, one of the nice thing about it, if you want to set the timer on things, this actually has a set periodic. This is actually a call you can use. Basically, it's a periodic timer to fire every however many milliseconds, and then you can have a handler to be called, at the time. So this is just an example, right? So, okay, first of all, to write a vertical, and by the way, it's not required, but it's good to kind of extend your abstract vertical, or you can write your vertical directly. But the suggestion is to extend your abstract vertical, because then you can override the methods, like override your start and override your stop too. In this particular case, I'm not doing the overriding the stop, just overriding the start. So in this case, simple example, I'll just set a timer for every 5 seconds in here. Then I use a lambda in here, then basically it's a handler. So all I'm doing now is just logging it and print out tick and like that. And then another example, it would be like using Vertex to create an HTTP server. And basically you can then do a, immediately this, you're making use of like functional style of programming. You chain all your calls together. You have a dot request handler and you use a lambda. It's basically take your this particular request, and I immediately, basically from the request, I get the response and then print out hello. Then I also then bind this HTTP server, bind it to the listener and bind it to port 8080. And that's all I'm doing. It's nothing like major in here. In order to instantiate, to deploy your vertical, all you need to do in your main is just you start off your control center. And that's all you need to do is doing a vertex.vertex, and that will start your control center. So your control center in here, all you need to do is deploy vertical. And then you can just deploy whatever you want to deploy doing a new, and that's how you can do it. So now if you run this, then all this code will be doing, and I won't be running it now because it's going to slow down my system, and I think we don't have as much time. But I have also done an example of a polyglot example too, and I showed it earlier. But the thing is, I just want to quickly show is that in order, this particular case is that I'm using this is a kind of API gateway. I can kind of filter all of the requests coming in, and basically then based on the request, I will direct all of these, kind of processing to different worker nodes. And these are different worker nodes are implemented as different flavor. So I have a deploy Java worker. So over here, I want to highlight, these are other things I read the configuration, and basically to deploy it, again, you use the control center, do a deploy vertical, and pass the name of your vertical. So in this case, if it's Java, I have API worker vertical .class.get name, and that's how I do it. And then that's what it is, right? So I then have, these are just, it's not really doing much, but I just want to demonstrate that. And this one is deploy Kotlin worker. So over here too, if you deploy it, you can just specify. All you need to do is deploy vertical, deploy Kotlin worker vertical. And then if you want to do JavaScript, you can actually do a deploy vertical and pass it the name of that JavaScript too. So these are like the different examples. So my Kotlin, it's kind of simple too. Over here, this is how I can do Vertex and using Kotlin semantics, right? So so doing an override my start and then basically vertex.set periodic, and that's how I'm doing it. And over here, yeah, then I write, I kind of interact directly with my event bus to publish these messages to, it said so often I'm publishing these messages to my, to the particular stream that I want to publish it to. And then the consumer is what it is doing in here. And the consumer is basically then send back the reply in this case and keeps track of some metrics. So that's a basic example. And JavaScript too over here is, again, over here I just do an event bus consumer, and that's how I do it. So, okay, so yeah, so that's kind of an example. I think I may be like at 7 o'clock or 7 o'clock, my time is top of the hour. I suppose it is probably I should then go to the, hold on. I should go back to my slide, I'm sorry. Okay, and I'll just play it again because at this point, I think I realized that I'm a little bit kind of over time, but if you're still here, thank you. I just wanted to say thank you to all of you for coming to my talk. And I like to also point out, this is how you can contact me. And there's also an IBM Cloud sign up. There's also the reactive design patterns that I was talking about. This has got a nice resource of if you want to read up on different reactive design patterns. And then this is, the different URL to the different resource you can find. And also we have an IBM Java newsletter if you want to subscribe to that. If you're interested in other topics too, we also have like AI, data science, analytics, and all these other things too. So, okay, so that's that. And then there's also these are the set of Reactive Streams resources. And again, as application programmer development, we just need to worry about using these libraries and not implementing this spec. So.